enjoy the comic. Not much to it, just a little bit of humor here. As far as the actual answer to the question, there isn't an actual answer to the question. We'll just go with what we've got there. So let's review electrolytes and non-electrolytes. Electrolytes are anything whose aqueous solution conducts an electric current. And a non-electrolyte is anything whose aqueous solution does not. So we've got electrolytes, non-electrolytes. The key is whether they have an electric charge or not. And we're going to take a look at that on the next slide. Examples of electrolytes. Anything we can test to conduct electricity. Tap water is a very weak electrolyte. It has some ions floating in it that it picked up along the path to your tap. So if it came from a well, it's got some dissolved minerals. Those are metal and nonmetal ions that it's picked up along the way. It's also in the pipes picked up some electrolytes. That's why I run the distillation machine in the back to help get rid of some of those electrolytes. A sodium chloride solution. When sodium chloride dissolves in water, it dissociates into sodium ions and chloride ions. Remember, dissociates is when an ionic solution splits apart into its ions. Ions are charged particles. Those are electrolytes. They'll conduct electricity. HCl is a covalent compound, but it ionizes. In other words, it's such a strong acid that it will force the hydrogen, the proton from the HCl, onto water to make hydronium. Think back, hydronium, H3O+, leaving a chloride ion. It's not an ionic substance. HCl is actually covalent, but it will force that hydrogen onto water to create charged particles. So HCl and all acids are electrolytes. Lactate solution lactate is a covalent compound, but when you put it in water, some of the hydrogens on the lactate will be picked up by the water molecules to make some hydronium ions, leaving the lactate ion. So it creates some ions. It becomes a weak electrolyte because most of it stays molecular. Only a few percent actually ionize to create hydronium. So it's a weak electrolyte. Non-electrolytes are anything without any ions or charged particles in the solution at all. So pure water, no ions, will not conduct electricity. Sugar solution. It dissolves, but it's covalent and doesn't actually ionize anything. It creates hydrogen bonds with water, but never actually ionizes the water. So that's a non-electrolyte. Same with ethanol. Ethanol dissolves in water because it creates hydrogen bonds, but the hydrogen, that proton, never actually fully transfers to the water to make hydronium. So ethanol is a non-electrolyte. Solid, NaCl. Because it's solid, the charges can't move. And electricity, an electric current, has to have moving charges. Solid, no moving charges, completely a non-electrolyte. On the other hand, if you melted sodium chloride, it's a liquid, those ions, the sodium and chloride ions, can move about freely. So you could conduct electricity through molten sodium chloride. However, that's above like 900 degrees Celsius, so good luck finding any metal electrodes that you can use with that. So again, here we're looking at the strong acids that completely ionize. Strong acids are HCl, H2SO4, sulfuric, nitric, hydroiodic, and perchloric acids. On your list of acid strengths of acids, we've got that list in the classroom and in your book. You can look and see it'll list which the strong ones are. Everything that's not a strong acid is a weak acid. And weak acids generally have about 5% ionization or less. So when we write them out, we do not write them as ions in the net ionic equation. We write them as whole molecules with the hydrogen still attached. Now when they react to the base, the hydrogen leaves. Strong acids we will always write as separate ions. So HCl will be written as H plus and Cl minus, or better H3O plus and Cl minus, to show what it actually looks like in solution. Because for strong acids, pretty darn close to 100% of it ionizes. Make sure you learn these strong acids. That's something that you have to have memorized for the final exam. As a quick review, the molarity calculation is moles of solute divided by liters of solution. So to figure this out, how many grams of sodium chloride are needed to prepare 1.5 liters of a half molar solution? Well, to find the concentration, the 0.5 molarity, that's going to be moles divided by liters, or X divided by 1.5. So to solve that, 0.5 equals X over 1.5. We multiply both sides by 1.5, and we'll get 0.75 moles of sodium chloride. Well, that's fine, but we asked for grams. So you're going to have to do a railroad tracks to change moles, 0.75 moles, into grams. And you can find the molar mass of sodium chloride, set up your railroad tracks, and find that. We'll go over the sample problem together in class. When you're working with dilution problem, the formula is molarity times volume of the stock solution, the original, equals molarity times volume of your final dilute solution. So if our initial concentration is 11.6, we're trying to find the volume of that original solution we need. So it would be 11.6 times X equals 3.0 times the volume, 250 milliliters. So 3 times 250 is 750 milliliters. And we want to solve for X, so we'll take 750 divided by 11.6 molar, and that will give us the milliliters of the stock solution that we need. Now, usually we deal with just liters in volume, but as long as you've got the same units on both sides for this, it'll work out fine. If you feel strongly that you need to change everything to liters just to stay consistent, go ahead and do that. So you'd have 3 times 0.250, and then that would be 0.750. So we take 0.750 divided by 11.6, and then of course you'd have to change it back to milliliters to figure out how you'd measure it in your graduated cylinder, because we don't have anything that actually measures in decimals of liters. That's why I'm lazy. We just leave it in milliliters. We'll go over this and work out the exact answer to this in class. So this sample problem is more like what you would see on a test. This involves everything we've done with stoichiometry and the molarity concentration, all this stuff. So if we start with 70.5 milligrams of potassium phosphate, we add it to a certain concentration of silver nitrate. We need to, write the molecular equation. We can do that. We know how to write the molecular equation. That means include everything as a molecule. Now to find the limiting reactant, again, we need to do 2 railroad tracks. We know how many milligrams of potassium phosphate we're starting with, and we will take it to the precipitate, because that's what we're always interested in. So you do your first railroad track from potassium phosphate to whatever the precipitate is. Now, the second one we're starting with, the other reactant, is silver nitrate. We're going to find the number of moles of silver nitrate using our concentration formula. Remember to change milliliters to liters. Once you have moles of silver nitrate, then you just do a 2-step stoichiometry, 2-step railroad tracks, to find grams of the precipitate. And remember, whichever one gives you less precipitate, that's going to be your limiting reactant. And that will automatically answer C. We'll work through this together in class, but these are all things you already know how to do. It's just a matter of putting all the steps together. And finally, this is a titration type reaction. We're neutralizing an acid with a base. So if we have 20 milliliters of sodium hydroxide of an unknown concentration, and we titrate that with sulfuric acid, and we know the concentration of sulfuric acid, it's half molar. We know how many milliliters of the sulfuric acid we used. The trick to this is to find how many moles of sulfuric acid we used, do a 1-step railroad track to find moles of sodium hydroxide, and then use the concentration formula to find, we've got moles of sodium hydroxide, we've got volume, divide those two things to find the concentration of sodium hydroxide. Again, we'll go over this exact problem in class together, but you should be able to do this. Give this one a try. Bring your work to class.